I want to take a few minutes and talk about Gibbs free energy. You may recall from your freshman chemistry, you calculated Gibbs free energy in association with chemical reactions. So perhaps you had a couple of ions and they bind or they are taken apart. Any type of chemical reaction, we're talking about changing or the exchange of electrons. In some reactions, as you know, will release energy. Other reactions, as you know, require the input of energy for the reaction to happen. Well, regardless of how much energy it takes for the reaction to happen or the amount of energy that is released if the reaction happens, you can calculate, you can quantify that release or taken up of energy. And we call that Gibbs free energy. And so we symbolize it as delta G. When the delta G is negative, that means the reaction has released energy. When the delta G is positive, that means the reaction has consumed energy. Well, we can apply this Gibbs free energy concept to movement of molecules across a cell membrane as well. Consider the situation where you have a molecule on one side of a membrane and then you have a quantity of molecule on the other side of the membrane. And if the molecule in some way can get across the membrane, if it's going down its concentration gradient, then the movement of that molecule down its concentration gradient is actually going to be releasing energy. If we had to move a molecule across the membrane and it was going up its concentration gradient, then that would require the input of energy for that to happen. So we have an equation that allows us to quantify movement across membranes, and it is this equation here. It's delta G is equal to RT natural log concentration in over concentration out. The R is the gas constant. You can see the units here, and we're going to say that the R is a 2. There's a lot of mathematics behind that, which I don't want to get into. We're just going to say that R equals 2. Of course, you know temperature is a factor, so we would have it in Kelvin scale, and so we know that 273 is going to be, or positive 273 is Celsius, so we definitely want to put everything in Kelvin, which we can. Then we have natural log, which we have right there, and then the concentration. Typically the concentration is going to be in millimolar, but as you'll note in the equation here, it doesn't really matter what the concentration is in terms of units as long as they're the same, because whether we're going in over out over in, it's a ratio, so the units actually cancel. We just need to make sure that both of those are in the same concentration, and then everything will work out. So if you work that out, you can actually quantify how much energy is being released or being taken up. Now, I want you to know this equation, but I'm not interested in you memorizing units or memorizing the R value or anything like that. I just want you to know what the relationship is. It's a fairly simple equation in this form. Well, let's apply this to glucose. Now, you can imagine that I have a cell here, okay, and there is my cell. And I have glucose outside the cell, and I have glucose inside the cell. So we're going to say that the glucose inside the cell is 0.5 millimolar. And then I have glucose on the outside of the cell is 5 millimolar. So that's quite a jump. So I have 10 times the amount of glucose outside the cell than I do in. And so our body temperature is 37. So we're going to, again, converting the scale, Kelvin. So we're going to say, of course, you got your 273 plus 37. So in Kelvin, body temperature is 310 Kelvin. So we have the numbers. Then it's just all a matter of going through and assigning it or figuring out its Gibbs free energy. Again, I'm going to be moving glucose down a concentration gradient. So therefore, it is going to be releasing energy. So you work that out, and you find out that given that concentration that I'm going to be releasing minus 1.4 kilocalories for every mole of glucose that goes down its concentration gradient. So it's an easy calculation. Now, if you really wanted to work with log 10 as opposed to natural log, you have to convert it by a number 2.303. Again, this is not something I'm interested in you memorizing. I'm just telling you or making you aware that you can have a 10-base version of this equation as well. Okay, so at this point, it's just kind of plug and chug. Now, I want to say something that I've alluded to before, which is glucose does not cross the cell membrane very easily at all. In fact, it's relatively impermeable to glucose. But glucose can go through a cell membrane if it has a transporter or a channel or something that helps it get across. We have a whole set of transporters in our cells that shepherd glucose from one side to the other side. But as we're going to see in a bit, the concentration gradient is going to be a factor in terms of how much energy these pumps have to either release or use to move glucose from one side to the other. All right, so now let us consider another situation where we have an active transport of glucose. Now, if the glucose is going down its concentration gradient, then this is going to be happening spontaneously because, again, it is releasing energy. But if we were to have to move glucose up its concentration gradient, then that's a completely different matter. And in fact, that's most of the time, at least in certain parts of my body, that's what is always the case. Consider two scenarios. Similar, but a little different. When I consume glucose, I eat the candy bar or the donut or whatever. I'm taking in or breaking down starch. But anyway, I'm consuming glucose. And that glucose is going to go, first of all, it's going to be broken down in my GI tract. And the job of the GI tract is to take that glucose and transport it out of the lumen of the GI tract into a cell. Now, here's the challenge. And that is I can't depend on simple concentration of glucose inside the GI tract or relative to the cell itself to move it. Because the object of the game for your GI is to remove all the glucose. So if I need to remove all the glucose, can you not say by definition that I am going to be moving glucose up a concentration gradient? So if I were to have a cell, okay, and this cell's job is to absorb glucose or take up glucose, and suppose this is my GI out here. Okay, there's my GI glucose. So, and I want to get all glucose or almost all glucose out of here, and I need to move it into the cell. Well, as I am absorbing it, the glucose level is getting less and less and less outside the cell, which means I'm having a greater and greater concentration gradient to where now it's taking more and more and more energy to move that glucose from the lumen of the gut into the cell itself. It would be a waste to be eliminating glucose through your GI tract. It wouldn't be very efficient. So your GI tract is pretty good at reabsorbing the vast majority of the glucose that you ate. The same thing is true in your kidney because, and we'll go into this later when we do renal, but you have filtrate in the kidney that ultimately becomes urine. And so we will learn later in the term that glucose makes it into the filtrate. Now, filtrate in the kidney is just simply the fluid that's going to become urine. You're going to change it, you're going to modify it, but the kidney's job is to take that filtrate and reabsorb all the stuff that your body needs, and then whatever left is urine. So the filtrate, or the pre-urine in your kidney, is filled with glucose. You don't want to eliminate glucose from your body through your bladder. So the kidney has to take all that glucose and then move it back into the body. And it has the same situation, where now I am having, glucose out here, and the kidney is having to reabsorb all that glucose from the filtrate. In this case, this will be filtrate. This is in kidney now. And you see the same challenge. If I'm wanting to get almost all of it out, I'm going to be pulling glucose against its concentration gradient. Again, requiring energy. Okay. So the way we do this is what we call active transport of glucose. So the glucose level in a normal body is about 5 millimolar concentration. So your 5 millimolar would be in the cell itself, 5 millimolar in the cell, and then the glucose in the filtrate out here would be less and less and less and less as it absorbs more and more of it, which means I am making the concentration gradient larger and larger. So what we have to do is we have to figure out a way of having enough energy to do that. Now again, I'm going to get into this later, because here I'm talking about proximal tubes and apical surface and basolateral surface. The apical surface basically is the side of the cell that is next to the filtrate. So I'll show you a little cartoon here. So I'll draw one here, I'll draw one here, and then the filtrate, which we would call kind of our pre-urine, is in a little tube there. So this is where our filtrate is. That's the yellow. And then the cell is making the tube here. So I have glucose here, and I'm trying to get the glucose into or absorbed from the filtrate or the pre-urine. But to do so, again, I got to go up a concentration gradient. I'll talk about proximal tubule, and I'm going to be reviewing this when we do renal. Anyway, so we have to move that glucose up a concentration gradient. So let's run through some numbers. So what is the free energy that we need to move glucose back from a tubular fluid? This would be the filtrate, to the blood. I'm trying to get most of the glucose back out of the filtrate, and I want to pump it out or reabsorb it until the filtrate final concentration of glucose is 0.005 millimolar. Let's just say that. So I have now a 0.005 millimolar, and I need to move it to a 0.5 millimolar, or 5 millimolar. So here's my concentration gradient. So the filtrate is this concentration in inside cell. Is this concentration. That's quite a concentration gradient. But we can take our handy-dandy formula and we can plug it in. So we just apply, and what you find out is, note this is a positive, which means that it is going to take 4.3 kilocalories per mole to move glucose against the concentration gradient if the concentration gradient is a 5 millimolar versus 0.005 millimolar if I'm moving it in that direction. Okay, well, we know there's no free lunch. So if the kidney or the gut cells in the GI, either one, if they're moving glucose against that concentration gradient, that energy has to come from somewhere. Well, how does that work? And again, I'm going to go in much more detail later in the course with this. Right now, my purpose is just to show you some numbers. But we have a sodium glucose transporter. So now I'm going to just draw another cartoon for you here. and a cell. And so what I have now is going to be a transporter that is designed, there's going to be my transporter here, and it is designed to move two molecules, to move sodium and to move glucose. So you may know from other courses that typically there's a lot more sodium on the outside of the cell and just a little bit of sodium on the inside of the cell. The sodium concentration gradient is fairly significant. Now what I'm also trying to do is I am trying to move glucose from outside the cell to inside the cell. And in this situation here, I am going to be moving glucose from a small concentration to a large concentration. So I've got a little bit of glucose here. Remember, that's going to be my 0.005. And then I got a lot of glucose here, which is going to be 5 millimolar versus 0.005 millimolar. So I need to move glucose from here to here, and I'm going to use that pump to do it. So that pump is going to be grabbing a glucose from the filtrate or the GI tract and moving it inside the cell up a pretty steep concentration gradient. Well, this particular pump also has the attribute of allowing sodium to go through as well. So actually what's going to happen is that I am going to take this sodium that's going down its concentration gradient, and I'm going to let that input energy into this pump so that it can move the glucose up its concentration gradient. So let's plug in some numbers and see if we can balance this energy checkbook. So as we've already talked about, this is a symporter. So sodium is going down its concentration gradient, and here I have outside is going to be 140 millimolar of sodium. So I just go ahead and put that in here, 140 millimolar of sodium. And inside is going to be 10 millimolar of sodium. So I have a nice concentration gradient there. The glucose, we've already talked about. So what we can do then is let's go ahead and punch in the numbers for sodium. Okay, remember I got 140 out, I got 10 in. I'm going to plug in, there's my 140, there's my 10, run my numbers, and I find out that when I allow sodium to go down the concentration gradient, how much energy will it be making available for that pump? And we find out that it is negative 1.6 kilocalories to do so. Is this enough to move a mole of glucose? Well, no. How much did we need to move glucose from here to here? We needed 4.3. Well, 4.3 is quite a bit less than 1.6. So simply taking a sodium molecule and letting it go and get down its concentration rate is not going to give me enough energy. Well, we have another factor. And again, I'm going to elaborate much more on this later when we do electrophysiology. But you may recall that sodium is also a charged particle. It has a valence of plus. You also may remember from freshman courses that a membrane has a voltage potential across it, and typically the inside of a cell is about 70 millivolts relative to the outside of the cell. In other words, there's a minus 70 millivolt difference. Inside the cell is negative relative to outside the cell if we're talking membranes. So another factor to consider. I have a positive valence. It is moving across the membrane. Remember, the outside's positive, the inside's negative. This is positive, so negative positive attracts. Therefore, I have the negative valence is pulling sodium in. Sodium is charged. So I'm actually releasing energy when that sodium is going across to the opposite valence. So that is an additional amount of energy that I can quantify. So let's take a look at an equation here that we have, and we can say the Gibbs free energy is equal to this, where Z is the charge of the ion, plus 1 in this case. F is that number there, which I could care less if you memorize. Don't do it. Just know that it's out there. If I had you do an equation like this, I'd give you that number. And then the Vm is going to be the potential difference. And again, for most cells, it's going to be about a minus 70 millivolts, with the inside of the cell being negative relative to the outside. So I can plug that in there and calculate it, and I find out that I am going to be releasing minus 1.6 kilocalories per mole every time a plus 1 goes down to to inside the cell, because it's attracting. So I can add this energy plus my other energy going down its concentration gradient, and I'm going to get now a total yield of 3.3 kilocalories per mole. So two things. One, the sodium is going across the membrane. It's going from positive to negative, so the negativity of inside the membrane is drawing the sodium in. Plus, the sodium is going down its concentration gradient, so I have two things that's going to yield me energy, and then when I add those up, I get 3.3. Okay, and so still I got a little bit of a problem, which is how much did I need to get this glucose across? 4.3. I am only at 3.3, so I still don't have enough energy to move that glucose. Well, interestingly enough, though, when you look at the pump itself, the glucose sodium symporter, what in fact happens is that every time that pump spins, it is bringing 2 sodium molecules for every 1 glucose. So if it is bringing 2 versus 1, so quickly a cell here, there's my cell, and so this is going to be my transporter here. All right, so I've got 2 sodiums going in for every 1 glucose going in. So now that I'm having 2, and again, concentration is the same, the voltage is the same, therefore I can double that, and I get 6.6 kilocalories per mole of energy made available. Now we're in a good place, because now I've got 6.6 kilocalorie of energy available with this pump, and I only need 4.3 to move the glucose, so now I have enough energy to push that glucose up its concentration gradient. Okay, so that's what that is. Now, another thing that we need to keep in mind is that as I'm moving sodium down its concentration gradient, you can't do that forever or you eventually lose its concentration gradient. And so I just want to remind you that we always have a sodium-potassium ATPase pump. So that energy is going to come from the burning of ATP to push the sodium back out as to maintain that concentration gradient so that I can then use it to transport glucose. So this is a theme that you're going to see over and over again. So not only are we dealing with this example here, glucose calculated in the Gibbs free energy, you have the same dynamic going on with amino acids. Again, if I'm eating the steak, I am absorbing all that, breaking it down in my GI, so now I have this amino acids in my GI tract, and then also I would have amino acids in my filtrate in my kidney. I've got to remove most of that, returning it to the body, which means by definition, the amino acid is going to be going up its concentration gradient. And so consider, for example, we have glutamate, one of our amino acids, and it has a charge of a -1. So considering here now, not only am I having an amino acid, and this, we'll just call it glutamate since we're dealing with the charge here. So I've got glutamate, which is an amino acid. And it's got a -1 charge. And what did we say the inside the cell was? -70 millivolts. So now I'm taking a negative, and I am having to move it across the membrane to another negative. And so that's going to be a challenge. Okay, so that move there, negative across to negative, I am now requiring energy to do that. Plus, on top of that, I'm going to have a lot of glutamate in here and a little bit here. So I've got two things that I have to consider. Again, you can run the numbers. What we're going to have is we got to calculate the amount of energy I'm going to need for the charge, and then the amount of energy I'm going to need. In this case, we're doing 20 millimolar on the inside the cell, 0.1 millimolar on the outside the cell for glutamate. So 0.1 millimolar. And then inside is going to be 20 millimolar of amino acid. So running all of that together means that I am going to need, when I have the charge and the concentration gradient, I'm going to need 4.9 kilocalories per mole to move that glucose across, to move that glutamate across. And again, just like we discovered with the glucose, I am using a Symport transporter. So let me go ahead and draw that again. So now I've got an amino acid that we have here. Okay, there's my amino acid there. And so I am having glutamate. Okay, it is going up its concentration gradient and again also against its electrogradient. But I'm also going to be having sodium out here that is going down its concentration gradient. So I'm going to get the energy I need for glutamate to transport. I'm going to get that energy from sodium. Okay, so again, if I'm needing 4.9, one sodium is not enough to do it. So typically these transporters needs 2, and so we're in the 6.6 range, which means that's plenty of energy to move the glutamate or any other amino acid from the tubular lumen in the kidney, from the filtrate, or the GI tract. So anyway, all of that to say that there is no free lunch. That if we're moving a molecule up its concentration gradient, and or we're moving a molecule against its electrogradient, in other words, if we're taking something negative and pushing it into a negative area, then those are going to require energy. And the energy has to come from somewhere, and one of the major themes that we see physiologically is that we're going to use a symporter to make that happen, and so we're going to be dependent upon a sodium gradient so that the sodium can go down its concentration, freeing up energy to move something else up its concentration. But again, no free lunch. How do you maintain that sodium concentration? By the sodium-potassium ATPase pump, which requires more energy, and that energy is coming from the form of ATP. Anyway, I hope you found that helpful.